Hi friends, a very good evening and thank you for joining in. Could you please confirm in the chat window? I have the chat window open on my phone here. Could you please confirm in the chat window if you're able to see my screen and if you can hear my voice? Because if both of those are good, we can get started. So if whoever has joined the session, if you can please confirm. Okay, audio and video are absolutely clear. Good. Thank you. Thank you for the confirmation. Good to know that there are no glitches whatsoever. Good. So let's wait for one more minute. As soon as it is 7 p.m., I'll get started with the session itself. Couple of announcements. Students have asked us about the new content and things like that. We just thought we'll make a few quick announcements and then get started with the session itself. Okay. Thank you, mentors. I think our mentors have also joined the session. So good to know that everyone is here. Our mentors will try to answer some general questions, even technical questions. Hey, yeah. So yeah, our team, others also are joining in. Good. Just give me a second and we'll get started. A couple of quick announcements and then we'll dive into the session. Good evening, everyone, and thank you for joining in. So this is the first session for COA, right? So it's 7 sharp. So let's get started. This is the first session for COA, or Computer Organization and Architecture. Right after this, we have 2 more sessions. So we will be able to finish COA in 3 sessions. Some of you have requested for general sessions. We'll try to accommodate a general session in the coming week or the week after that. We'll surely do those. Okay, so don't worry about it. Couple of quick announcements. After COA, just giving you a heads up, we will be doing DLD problem solving sessions. Okay, digital logic design. So just wanted to give you a heads up. Those of you who are preparing something now. So after COA, we will do DLD, number 1. Then as far as the new content itself is concerned, so as we mentioned, we have shared a very detailed document with where all some of the content in the new syllabus is already covered and where all we need to do more content. It is in general aptitude where there is maximum content change, some content change with respect to compiler design. Some of these concepts we have covered, some of it we are yet to cover. Small change in operating systems. Most of the changes for OS, we have covered it, but we thought we'll do one more video on this. So we will be adding new content for all these 3 subjects and we'll do it by August 31st. So by end of this month, all the new syllabus changes. Again, OS and CD, OS is the smallest change. CD is the second smallest. General aptitude will take more time because there are more concepts and we have to take inspiration in terms of questions, in terms of the quality of questions from other exams that IITs and IISc and NITs conduct, right? So again, all the removed concepts, mostly from computer networks, concepts which are removed from GATE 2021, in our course videos, they will be marked as optional. We are still doing this process. We're being very careful. We're also being a little conservative here, just to keep any concept, even if you think it is there, right? We're just being extremely careful here, okay? So any questions you have, we strongly recommend that you reach out to us at gatecsc@appliedcourse.com. You can just go to our website, gate.appliedcourse.com. You have all the information here. Please reach out to us for any general queries, even technical queries. We'll try to answer. Of course, we give first preference to our course enrolled students, then to our test series enrolled students, last to other students. We have to give priority there. So again, in this session, let us focus on problem solving. Again, our mentors will try to answer some questions in the chat window, but anything we could not answer because of time constraints, feel free to email us so that we can provide much more detailed responses over email using audio replies or even using text replies, right? So let's get started with COA1. These are some quick updates that we wanted to cover before we start the session. Okay, so this is the first session for COA. We have 2 more sessions. We have already announced the timeline for those 2 sessions. The second session will be next Wednesday. The third session will be next Friday. Okay, let's get started, guys, now. Okay, so here comes the first question. Again, we have some MSQs also, right? So some MSQs are also there. So let's solve this problem. There are a couple of questions that I'll answer anyway in between these questions. Simple questions. We're starting with some easy questions. We have one MSQ also in this set. Again, as we mentioned earlier, we'll be adding MSQs into our test series also. Okay, please focus on solving the problems because that's our purpose here. Any questions you have outside of the concepts that we are solving now, please feel free to email us. Okay, a good chunk of you have put in your answers. Good flow. Getting started. Again, we wanted to warm up with some simple questions, then we'll go to slightly medium questions, right? Okay, most of you got it right. The answer here is 600. It's a very straightforward question, right? So let's solve it. So what does it say? An instruction, many of you got it right. I think all of you got it right. An instruction is stored in location 300. So this is your memory, right? So in 300, you have the instruction stored with its address field at location 301. So your opcode is at address 300 and your address, right? Your address is in 301. The address field has a value of 400. So the value here is 400. A processor register R1. So there is a processor register R1 that contains a number equivalent to 200. Evaluate effective address if the addressing mode of the instruction is indexed addressing with R1 as the index register. So if you just know what is, so how do you compute effective address? If you're using indexed addressing mode, you take R1. This is like the base address, right? To this you add whatever value is here, you get 600. So if you just know what is the definition of an index register, what is the definition of an effective address with respect to indexed addressing mode, you can answer it in like 10 seconds literally. And that's what many of you have done. So easy peasy question, very easy just to warm you up today. Okay, so let's go to the second question now. Again, this is also a simple easy question, but just be slightly careful here. Okay, here comes the second question. Most of you got the first question right. Second question, slightly be careful here. Again, we always start with easy questions and goes to slightly more medium level questions as we progress. Okay, just be careful here. Be slightly careful here. It's also an easy question. You have to be slightly careful with the number of bits for addresses and opcode. Again, please try to fill in the blank. Please try to write the number here. Please try to write the numerical value as if it's a fill in the blank question. I think I didn't mention that. Please try to fill in the answer here as a numerical answer. Some of you are writing numerical expressions. Please fill in the blank. Okay, think of it like a fill in the blank type of question. Okay, because you have to do that in the actual question. So you could use a calculator, obviously. In Gate also you're allowed to use calculator. So just use it and let's put in the answer. Again, COA is easy. If you know the concepts, COA is actually very scoring. If you know the concepts. Okay, I see most of you putting in the right answers, most of you. Again, just think about it. See, if you just know, that's what the beauty of COA is. If you know the concepts, again, this is an easy problem, obviously. So I think I don't see anybody, I think all of you got it right. All of you seem to have gotten it right. So, okay, good. We are starting on a very good note. I don't see any wrong answers submitted here. So that's good to know. Okay, cool. So let me try to answer this question now. First and foremost, a computer has a 32-bit instructions. So your whole instruction is 32-bit and 12-bit addresses. So the addresses are 12 bits. if there are 250 two address instructions, look at this, there are 250 two address instructions. So how do the two address instructions look like? One address. So if you notice, this is your address 2, you have address 1, and you have opcode, right? And each address is 12 bits. So this takes up 12 bits, this takes up 12 bits, 24 bits are taken up. There are 8 bits left for the opcode, right? Now it says there are 250 two address instructions. So with the 8-bit opcode, you can create 256 Boolean combinations or binary combinations, right? With 8 bits. So with 8 bits, you have 256 combinations. 250 of them have been taken up by the two address instructions, which means you are left only with 6 more. So how many one address instructions can be formulated? Since 250 are taken, only 6 8-bit strings are available for your one address instructions. Okay. So now let's try to construct one address instructions here, right? Now 6 bits are left here for you. Okay. So what do you have? You have 6 bits here, right? Okay. So your total length. Okay. Let me write it down. Sorry. So let's look at this pattern here. You have, so from these, so you have 8 bits, 12 bits and 12 bits. This is how we broke it, right? From this, right, we have only 6 possibilities. But since this is one address instruction, you only need to have one address. These 12 bits for these 6 possible combinations, these 12 bits can also be used for opcode because it's a one address instruction, right? So total you have 6 into, you can create 2 power 12 combinations here. So the answer here is 6 into 2 power 12, right? And which you simplify, you can just put it into a calculator, you'll get 24,576. Again, some of you have input this answer, which is 6 into 2 power 12, which is also correct. But if this was a fill in the blank type of question, you just do this, right? So again, here remember that the question says how many one address instructions are possible. In one address instruction, only you will have one address. Rest of these bits can be used for the opcode. So for the opcode, the first 8 bits will only take these 6 combinations. The next 12 bits can take any possible combination. Right? That's how this works, right? Very simple concept. Okay, so let's go to the third problem. This is also an easy question. This is about creating a memory chip using decoders. Rajesh is asking, is everything in COA complete? Yes, we have more than what is needed for GATE actually. So don't worry about it. In all of our courses, like even though some syllabus has changed for OS and CD, some of it was covered by us because we are conservative with the syllabus in the sense that we try to add even if we think there is a small probability that a question from that topic can come. Again, this is also an easy question. If you know about the basic memory organization in terms of using a decoder for RAM chips, this is a straightforward question. This is just about basic addressing. Okay, I see different answers now. Okay. Again, I see 2 different answers that people are putting it in the chat window. So just rethink your options carefully. Just think about your options a little carefully. Oh, I see 3 different options. So just be careful with your answers. You could correct it. Some of you are putting in A, B, and C. So just think about those options carefully. Again, speed is not what matters right now. Accuracy is. GATE has never been about speed. It's been about not doing silly mistakes and being careful with the concepts. Okay. Thankfully, a good chunk of you got it right, but some of you got it wrong also. Again, I see all the three answers, A, B, and C. Thankfully, nobody is saying D. That's good. Again, be a little careful here. It's very easy to get confused between A and B. I can see that mistake that people are making. Anyway, so let me get into the solution itself. Straightforward, easy problem if you know the concept. The total memory that we want to create is 128 kilobytes and everything is byte addressable. Unless otherwise stated, one word equals to 1 byte, right? In all of COA and digital logic design, unless otherwise stated. So you have 128 kilobytes here. So let's write it down. And what are your RAM chips? Your RAM chips are 512 cross 8, right? Which means each RAM chip is 512 cross 1 byte or 8 bits, right? Each of them is 8 bits or 1 byte. So how many RAM chips do we need first? Let's compute that. This is the total memory. This is the size of each RAM. So this is 2 power 7. Kilo is 2 power 10 bytes. This is 2 power 9. 8 bits is 1 byte. Right? These many bytes and these many bytes. Now if we simplify this, 17 minus 9 is 8. So we need 256 chips now. That part is clear. So which means option A can be correct, option B can be correct, option D can be correct. C can't be the option. First and foremost, very simple to, again, this is your standard MCQ. This is not an MSQ, right? So first and foremost, you got rid of it. Now you have 256 chips. So if you think logically, look at this. You have chip 0, you have chip 1, so on and so forth, chip 255. You need 256 chips, right? Now each chip has an enable button typically, which activates the chip, right? Every RAM chip has an activate button, right? Or an enable button, it's also called as. So now to select one of these 256 chips, what is the decoder that you need? You need an 8 cross 256 decoder because look at this. You will take 8 bits in. You'll take 8 bits of address in here and you'll select one of these 256 chips by connecting this to a chip enable line, right? Because you have 256 chips here. And because you have 256, you need 8 here. 7 won't work, right? Again, many of you have written answer as A. Look at this. With a 7 cross 128, you can't select 256 chips. To select 256 chips, your decoder should have 256 outputs. If it has 256 outputs, it needs to have 8 inputs. So option B is the right option here, not option A, right? So I think some of you got confused with that a little. So option B is the right option here. Certainly not C and D. Okay, cool. So let's go to the fourth problem. Okay, now we are getting into the medium territory. This is a very, I enjoyed solving this problem. It was a fun problem, not hard. By no means it's hard. If you know the concept of basic memory addressing, this is straightforward. Slightly, just like the previous problem, but slightly more intricate. Slightly. That's why it's tagged as medium, not easy. This was a fun question. I enjoyed solving it. Again, please be careful that the word here is 16 bits, right? So that's what you have to be a little careful with. This question is very similar to the previous question, except that the word size has changed and there is a little bit of intricacy because of it. In COA, always draw diagrams. It's extremely important to visualize an architecture or a chip. Because the moment you start drawing diagrams for COA, you'll stop doing silly mistakes. That's what we have done extensively in the course videos also. For every problem that you encounter, we draw a diagram so that you get the whole architecture visualization. One of the students is scared about GATE 2022. There is so much time to improve. There is so much time to learn and become good at it. Don't worry about it. It is the small amounts of effort that you put consistently day in and day out that'll give you results. Okay, I see. Fill in the blanks are fun because there are multiple options that people will come up with. I see multiple answers here. Interesting. Our mentors are also putting in some suggestions. Good, good, good. I'm happy that many of you are focusing on the problem solving part now. Very happy. Any questions you have, reach out to us over email. We can give you much more detailed answers there. And we are happy to help anybody whom we can. Okay, I see various answers. 1, 9, 16, 8, 19, various answers. Again, if you just know how to draw these diagrams and think through it, it's actually fairly simple. Let's wait because it might take some people a few more seconds to realize what's the problem like. So let's give everybody a little chance. Okay. So again, the same answers: 1, 9, 16, 19, 8. Okay. Okay, so let me get into the solution since we have spent some time with the problem itself. So RAM chip has a capacity of 2048 words of 16 bits, which means it is 2K cross 16 bits. Okay, this is what the RAM chip is. This is the RAM chip. Now, the number of 3 cross 8 decoders with enable line needed to construct a RAM of 128K cross 32 bit, right? From 2K cross 16. 2K cross 16 is what you are given, right? So the number of 3 cross 8 decoders that you need, that's the question. First, let's compute the number of chips that you need. You have 128K cross 32. That's the total memory that you want to create, right? What is the size of each of your chip? 2K cross 16. So what will this be? 2K, this is 64, this is 2. So you need 128 RAM chips. Look at this. First and foremost, you need 128 RAM chips. That's the first part. Now, because you need 128 RAM chips, the second thing that you should be very careful about in this problem is, here the word size is 16 bits. Here the word size is 32 bits. So which means when you're organizing these RAM chips, you have to do them like this: 2K cross 16 and 2K cross 16 side by side. So that when you enable this chip also gets enabled. And you can generate the 32-bit word here, right? Look at this. Look at how we are organizing this. Because each of your base RAM chips are 2K cross 16, but you want a word size of 32. You want a system where whenever this chip is enabled, this chip is also enabled, so that you can generate a 32-bit output, because this 16 will get concatenated with this 16 and generate 32, right? That's important. Now you can create these concatenations: 2K cross 16, 2K cross 16. Okay, this will again generate a 32-bit output. How many such do you need? Look at this. Each row here has 2 chips, and you need a total of 128 chips, which means there will be 64 rows here. There will be 64 rows here, right? That's the first thing. Now you want to create, so remember that whenever this chip is enabled, this chip also will get enabled, because all these 16 bits and this 16 bits should get concatenated and be generated as output, right? So you need a way to select these 64 lines. Think about it as 64 lines, right? This will enable, this will also enable, this will enable, it will also enable this, and so on and so forth. You need some way to enable 64 chips basically, or 64 lines you have, which you need to enable. But all you have is a 3 cross 8 decoder, right? Imagine instead of a 3 cross 8 decoder, if you had a 6 cross 64 decoder, you just need one decoder and you're done. But all that we are given to us is 3 cross 8 decoders, right? So imagine I have a 3 cross 8 decoder here, which generates only 8 output lines. So I have one more 3x8. How many such decoders do I need? This can only be connected to 8 of these lines. This can be connected to 8. So on and so forth. I need 8 decoders here to connect to 64 lines here. Right? And there are 8 here, which means I need one more 3x8 decoder which connects to each of these. So to select these, again, the important aspect here is that you have 64 lines that you need to activate. And all you have is 3x8 decoders. So you have 8 decoders here and you have one decoder here, all of them 3x8 decoders. So you need a total of 9 3x8 decoders to construct this RAM chip, or to construct a memory of 128K x 32 using 2K x 16s. Okay, so always try to draw these diagrams. Those are the ones, these diagrams will help you give a big picture view, and you'll not make silly mistakes using them because of this, right? So I strongly recommend you draw diagrams. Again, the reason this problem is medium and not easy is just because of the word sizes. This chips are 16-bit, this chip are 32-bit word size. So it's just that small trickiness that you have to be careful with. Okay, cool. So let's go to the next problem now. Again, a good chunk of you got it right, which is very encouraging. Okay, let's go to the 5th problem now. This is all about indexed addressing mode. This problem is very easy to make a silly mistake on, so please be careful. The reason this is medium and not easy is because we think many students will make silly mistakes here. So somebody asked how to make COA one of our strong subjects. Actually, when I was preparing for GATE, COA was one of our sorry, somebody has a question. AC means what is loaded into AC? Accumulator, yes. Yes, AC is accumulator, yes. Sorry, we should have called that out clearly, yeah. Yeah, so the way I became good at COA is I would draw these diagrams that I'm drawing now. Even when I was solving these questions just before the live session, I would draw diagrams. So translate all the concepts into diagrams. The concepts of COA are actually very simple. It's just that people think of these as overwhelming, but if you start drawing diagrams, that's what has helped me become very good at this subject. In my BTech first 2 years or so, even in half of my 3rd year, hardware subjects and system subjects were my favorite subjects. I enjoyed COA, DLD, because I was understanding how a computer works, microprocessors. Slowly it changed to more mathematical subjects as I was getting closer to my graduation. Anyway. Okay, people are mostly putting in C or D. Yes, that's a trap. Yes, most people will either put in C or D, and that's the trap. That's what makes this question not easy but medium, because that's a trap that many students will fall into. Okay, a good chunk of you have already answered it. So let me explain the solution, right? So assume that the following values stored in memory and R1 storing 200. So you have R1, this is the register with a value of 200. These are your memory values. Okay. What is loaded into AC using the instruction load 1000 when using indexed addressing mode? That's all there is, right? So when you're using indexed addressing mode, what is your effective address? Your effective address is indexed using the 200, right? So your effective address is 200 as your base address, or the base of the index, plus 1000. So your effective address is 1200. Some of you will just go ahead and tick C as the answer. That's not the answer. What does the question say? The question says, the question clearly says, what is loaded into the accumulator? What will be loaded into the accumulator? Whatever is stored in the effective address. So your accumulator will get the value of whatever is stored in memory in this effective address. What is this? memory, what is stored in address? 1200, right? So what is stored in 1200? 800 is stored in 1200. So 800 is the right answer. So a lot of people who have given C as the answer have put in effective address. The question doesn't ask us about effective address in indexed addressing mode. It asks about what is stored in the accumulator at the end of the day. Accumulator stores whatever is stored in memory in the effective address. That's why 800 is the answer. It's a very small catch where some of you have made mistakes, right? Cool. So let's go to the next question. This is an MSQ. Okay, we are clearly calling it out. It's an MSQ. So please be careful. Please be careful here. This is an MSQ. We are clearly calling it out. We mostly think that GATE will also call out MSQ questions or put it in a separate section altogether. They will surely call out MSQs. So don't worry about it. So multiple options can be correct here. Those of you who don't know what an MSQ is. There are no negative marking in GATE for MSQs starting this year, and partial marks will not be awarded. So you have to get all the options correct. Again, draw diagrams. See what is there in the memory. Go step by step here. Okay, people have started putting in the answers. Again, one of the students has a question that he's concerned about the placement scenario this year and that is distracting his GATE preparation. Don't worry about it. Don't worry about things that you don't control. Do your best on things that you can control, like GATE preparation. That's all in your hand. The examination is going to happen and it's all in your hands to do well. So don't worry about external factors that you don't control. Okay. Okay, I see a couple of options that people are putting in. Again, as an interesting thing, GATE can say a question is MSQ, but only have one of the options correct, because one or more options should be correct, right? So that's also a small tricky thing that GATE might do to get people to fall into the trap. Again, somebody is asking, what does this mean? This is the typical syntax that used for indexed addressing mode, with the base address as RS and the memory location as 2000, right? So this is the typical syntax that you use for indexed addressing mode. Same thing here also. This is the indexed addressing mode. Okay, some people are saying B, some people are saying C, some people are saying D, some people are saying both B and C. Just draw diagrams, folks. One of the students, Arpit, says diagrams makes it easy. It makes it dead easy, trust me. Especially with COA and DLD, diagrams matter a lot. Okay, a good chunk of you seem to have answered. So, most of you are going between B, D, or B and C. Those are the three options that I see a lot. Okay, so let me get into the solution anyway. So what's the question here? The memory locations 2000. So let's write down this. I always try to draw. That's what helps me enormously. 2000, 2001, then you have 2020, right? Have the values 14, 2 and 32 respectively before the following program is executed. Okay. Move I, right? It's basically move immediate. So whatever is there 1, that gets moved here. This is immediate addressing mode, right? So now what happens? After this, what happens? RS contains 1, right? First thing, because it's this 1 is moved to this, right? It's immediate addressing mode. Load from memory. Okay. So here this sort of syntax basically is used for indexed addressing, right? So what does it say? Into RD. So the final result will get stored to RD is RS. What is there in RS? RS contains 1. You have 2000. So 2000 plus 1 is 2001. So whatever is there in memory address 2000 plus 1 will go into RD. So what is there in 2001? 2 is there. So RD becomes 2. Right? Second step. Third step. It says add immediate. So what does that mean? You're going to add whatever is there in the immediate value. So this is immediate addressing. RD, whatever is there in RD. So RD becomes RD plus 2000. What is RD? RD is 2 plus 2000. So this becomes 2002. Right? Next. Store. Okay. Store. Look at this. What does it say? Store. Now what is it storing? It is storing 20. This is immediate addressing mode. 20 is being stored in this indexed address. What is this indexed address? Look at this. Memory of 0 plus RD. What is there in RD? 2002. This whole thing you're going to store 20 because it is immediate addressing. It says, right, store immediate, right? So it is going to store 20 in address 2002. So initially we did not have this. In 2002 it is going to store 20, right? So that's what it's doing. Okay. So now let's go to the options one by one. Which of the following statements is true? The question says true. So let's be careful. Memory location 2000 has value 20. No, because 2000 has 14. Memory location 2001 has 2. Yes, this is true. Memory location 2002 has value 20. Yes. Memory location 2001 has value 20. No. So B and C are the right options. Right? Again, here there are a lot of addressing modes that are getting mixed up. So you have to be careful here. Right? So this is immediate addressing. This is indexed addressing. This is immediate addressing. This part is immediate addressing. This part is indexed addressing. Right? That's what you have to be careful with. So this question is interesting because all these things got mixed up well. Okay, cool. So let's go to the next question now. This is also a simple question. You have to be slightly careful here. Because now we have to know how program counter, instruction register, memory address register, all of them work to get this answer correct. So one of the students says that when a question is in the previous exam question pattern, he's able to solve, but new questions he's not able to solve. I think the problem there is when you're solving or when you're learning concepts, you're not breaking down the problems into the core concepts. Probably you're trying to remember how to solve a specific type of problem. That will not help, right? Always translate any problem that you're solving to the core fundamental principles. Right? Again, in COA, just go to the core. If you know the foundational principles, translate every problem to that. Then you will not run into this problem. Okay, people are putting in the answers. So let's see. Okay. Again, just be careful about what should PC hold, what should IR hold, what should MAR hold. In case you are not sure, PC is program counter, IR is instruction register, MAR is memory address register. In case some of you are stuck with those terms. Those are standard terms used in whole of computer architecture and microprocessors. Okay, people are going between option B and option C. See, as we are coming closer to the exam, I mean, we are still like what, almost 6 months away from the exam. But still, I see significant improvement in the answers from students. That's very encouraging. See, that's what happens, right? You stick to the disciplined regimen. Over time, your answers will improve. I see significantly more correct answers nowadays than I used to see in these live sessions. Even just 2 months back. Just 1 month back also, right? We have close to, yeah, somebody says 141 days. Yeah, good. Thank you for that. So close to 5 months, give or take, right? So I'm happy to see that more and more students are giving more correct answers now. And that's what happens, right? You stick to the problems, start solving them. Over a period of time, your problem solving skills will improve. Very encouraging. And I also see that more students are joining these sessions, which is also very encouraging to us as compared to even just 1 month back. So cool. Okay, a lot of students have put in the answers. So let's get into this. Okay. So, okay, you have address So this is add R1 comma A is stored in the memory location 4004H, where H stands for hexadecimal. So in this 4004, this whole instruction, okay, this whole instruction is stored in the memory location. R1 is a processor register. Cool. A is a memory location. Very good. Thank you. Okay. A is a memory location with address 4000C. So A contains 4000C. I'll just skip the H part. I know that these are hexadecimal numbers. So if I have to add or subtract, I'll be careful. Each instruction is 32-bit long, which means 4 bytes long. Right? Each thing is 4 bytes long. What will be the value of program counter, instruction register, and MAR during the execution of this instruction? Very good. So first and foremost, let's start with PC. Okay, this instruction is in this address. It's starting in this address. Okay, the starting address is 4004 R1 comma A. This whole instruction is there. And we know that each instruction is 32-bit long, which means the next instruction will be 4 bytes away from it. At 4008 is the next instruction, right? Because there is 4 bytes gap here, right? Which means your program counter will always point to the next instruction that needs to be executed. So your PC will point to 4008. So first and foremost, PC is 4008. So this can't be the answer. None of the above can always be the answer. So you have to be careful. Okay, so PC is 4008. Good, one problem solved. Let's go to IR. Now what should IR be? IR consists of the instruction register, right? IR should consist of the instruction register. IR basically is the instruction register in which the current instruction that is being executed should be stored. Right? The current instruction should be stored. What is the current instruction? Add R1 comma A. This is what should be stored in the instruction register, right? So add R1 comma A. So this is what should, see, this is correct. Okay, so this is your PC, right? This is your IR. So this can't be the answer, but you have to be careful because none of the above is also there. If this is incorrect, then you have to go for none of the above. So A and B you have eliminated. Last comes the memory address register. Okay, so what is stored in the memory address register? Remember that in this R1 is the processor register, A is a memory location. So when this instruction is being executed, the operand here, this is the operand, right? This is the operand which corresponds to the memory location, right? So MAR should consist of the value of A basically, Look at this. We are told that look at this. We are told that A is the memory location with address 4000C. So MAR will contain A, which means MAR will contain 4000C. Of course, in hexadecimal. So this is PC, this is IR, this is MAR. Done. So when a line of instruction, or when one instruction is executing, if you know what should be there in PC, if you know what should be there in IR, if you know what should be there in MAR, this problem is literally, you can solve it in 1 minute. You just have to know what should be there when a program is executing. That's all. Right? Otherwise, it's a fairly straightforward problem. Okay, so the right option here is C. Cool. Let's go to the next problem now. Okay, looks little lengthy, but don't worry. It's actually, sorry. This is an interesting problem. Okay, this was a good problem. I enjoyed solving this. This is also a problem where it's very easy to make silly mistakes on. Again, this problem is little lengthy, so please read it very carefully. If it takes more time, let it take more time. That's okay. This is slightly lengthy problem and you have to be careful here. It's very easy to make a silly mistake on this. I almost made a silly mistake while I was solving this before this session. I think this is the most exciting problem of today. I think the next problems are easy. Yeah, I think this was my favorite problem of today because I almost made a mistake here. Okay, people have started putting in the answer this quickly. Wow. Was this the answer for the previous question or this question? Again, this is slightly medium to hard type problem. This is not actually hard, but it's not that simple medium also. So it's okay. As I told you, this was the best problem of today's session. I mean, at least I felt that. Some people may disagree. Again, read every piece of information that is given to you. If you read it carefully and if you think through it, you will not make a mistake. I don't remember solving a similar type of problem earlier, so this was fun. Okay, some people have started putting in the answers, so just please think about it carefully. It's okay to correct yourself. Speed is not important. If it takes 5 minutes, let it take 5 minutes. That's okay. Okay, I see like A, B, D. Okay, somebody should say C and then we have all the 4 options here. Again, as I was telling you, it's very easy to make a mistake on this. So please double check your answers, folks. Please double check your answers. Take it as a hint for everybody who has answered till now. Again, many people are falling into a trap here. These options have been given to make you fall into a trap. So please be careful. Our mentors have designed, I'm very happy with our mentors who have designed a very interesting question. Okay, people are, oh, somebody says C also. Okay, so A, B, C, D, all 4 options are here. Take your time, it's okay. Correct your answer if you have to. That's okay. Take your time. Again, people are going between A, B, C, D, all 4 options. I'll wait for a few more seconds and then I'll go into the solution, because this takes a little while for me to explain everything carefully. Most of you are going between A, B and D. Mostly between A and D. Some of you even B. Yeah. Few of you D. Okay, so let's get into the solution. Some of you have started putting in more detailed answers also. Good to see that. But anyway, gate is only objective, not subjective. But that's okay. I'm happy about it. Okay, cool. A processor instruction set consists of 200 instructions, where the instructions encode both all this stuff. Okay, I hope you have read this question. I've read it. I know this for sure. You have 0 operand, 1 operand and 2 operand instructions. You have 64 registers, 1 gigs of addressable memory, and an immediate data. The immediate data can lie between this negative number to this positive number, a total of 2 million values, right? Or 2 mega, or basically 2 into 2 power 20 values. Okay, and assuming we have no more than 1 memory reference, right, in which will be direct memory reference in any instructions, what are the range of instruction lengths in terms of bits from smallest to largest? Okay, so smallest is the first easy thing to solve, right? Look at this. The smallest thing will occur if you have 0 operand. So if you have 0 operand, which means you only have the opcode and no operand per se, right? If you don't have any operands, then the instruction will only contain just the opcode, nothing else. And you have 200 instructions. Look at this. To encode 200 instructions, you need 8 bits. And that's because 2 power 7 is less than 200, which is less than 256, which is 2 power 8, right? So you need at least 8 bits to encode 200 instructions, right? So if you have only 0 operands and the opcode is anyway 8 bits, so the smallest length instruction will be 8 bits. So you can completely rule out C. First problem, right? So it has to be A, B or D. That part is simple. Most of you got that very easily. Very good. So this is ruled out. Now let's go for the largest size. That's where things get a little tricky. Okay, so what is the maximum instruction size that we have? Look at this. What is the maximum instruction that we have? Our max instruction has an opcode, right? Opcode is 8 bits, right? Then you have, it says clearly that assuming we have no more than 1 memory reference. So you have 1 memory reference. And it is clearly given to us that the memory is 1 gigs, right? What is 1 gig? 1 gig is 2 power 30, right? So which means this direct memory reference, and it also clearly says it's direct memory reference, which means to directly reference a 2 power 30 gigs of memory, you need 30 bits, right? And you can have, the maximum size you can have is 2 operand instruction. This is 1 operand. The other operand now can be a register, or it could be immediate data also. It could be register or immediate addressing with immediate data. If it is registers, let's see, if it is registers, we have 64 registers. To address 64 registers, you need 6 bits. If it is immediate addressing, look at this, it also says you could have immediate data. Immediate data, the range of these values is 2m. So again, in your instruction, if you're writing these 2 million possible values, right, 2m, 2 mega, 2 into 2 power 20, right? So that is 2 into 2m is 2 into 2 power 20, which is 2 power 21. You need 21 bits here. So imagine now. So some of you have gotten the answer slightly differently. If you notice, 8 plus 30 plus 6 is 44, right? 14 plus 30, 44. Some of you have gone with this option, which is incorrect, because the question says, what is the largest? What is the range of instruction lengths in terms of bits from smallest to largest? The largest will not happen if you have a register. The largest will happen if you have an opcode, a memory reference of 30 bits, and an immediate addressing of 21 bits. Then what do you have? You have 51 plus 8, which is 59 bits. So B is the right answer here. So this question again uses all the addressing modes. You have register addressing, you have immediate addressing. Again, it's a very interesting problem from that perspective. I almost went for the answer 44, but then I realized that there is immediate data also. I also almost fell into that trap, and I was about to almost put D as the answer, but then I realized, why was this information given? Was it given just to trick us? Then I realized, no, there is immediate data also possible. So immediate data requires 21 bits. So the answer is B, right? So it's one of the fun questions of today. Cool. Let's go to the ninth question. Sorry, ninth question is easy. Yeah. Cool. The ninth question is fairly easy. Again, please read the question carefully, especially this highlighted part. This is an easy question. If you know the accumulator based architecture, this is a straightforward question. Okay. Good. It's an easy question. This was just given to recap your knowledge of accumulator based architecture. Most of you have started putting in the answers. Cool. Yeah, most of you got it right. It's literally, the answer is 4. All of you got, I think, I don't see anybody who got it incorrectly. Good. Easy question, just as a quick recap, right? So let's write the minimum number of instructions that you need, right? So it's an accumulator based architecture. So everything goes into the accumulator basically. So first this is what you want to evaluate numerically. So first what do? You load B, right? Then what happens? B goes into the accumulator. Then all operations will happen on the accumulator as one of the operands. Then you can say add C. So what will happen now? This will create B plus C into the accumulator, right? Then you do, so B plus C is done. So you can do div D now, right? So if you do div D now, what happens? Then the accumulator now consists of B plus C divided by D. Some of you stop here and write answer equals to 3. That's a silly mistake that some people fall for. But the expression says A equals to, which means this resultant you have to store it in A. So that step is also important. Store into A. So what happens now? Everything that is there in the accumulator gets stored into A. Right? So, or the memory location. So here ABCD are memory locations. Right? So some people stop it here, but please don't stop it because you have A on the LHS. This result has to be stored in A. So 4 instructions. That's all. Fairly simple problem. Right? So let's go to the next problem. Okay. This is okay. This is fairly not that hard actually. This is also easy. Again, some questions that we may not be able to answer by going back to previous questions. Please shoot an email to us and we'll try to resolve your question, right? So again, I don't want to jump between answers because that'll create the flow, that'll break the flow for other students, right? So anything that you're not sure of or anything that you want to discuss further, please shoot an email to us and we'll clarify. And if there is an error on our side, we'll correct it. We might overshoot by a couple of minutes, but let's solve this problem and then we can pack it up for today. This is easy. I mean, slightly tricky, but easy. Okay, I see a bunch of you putting in your answers. Good, good, good. Quick, fairly quick, guys. I mean, I'm happy. Fairly quick. In 2 minutes, I started seeing answers. Very good. So, speed is never a problem. That's what I keep telling people. It's a conceptual clarity that's important. Good. Oh, all of you are putting in answers. Very good, very good. Good. I mean, I'm enjoying the session as much as everyone else because I see so many students getting correct answers and improving over time, because I recognize some of these names that I've been seeing in these live sessions for the last few months, and I see some of you have improved significantly. Cool. Very good to see that improvement. Just stick to it, you will improve. Cool. Most of you got it right. The answer here is 28. The answer here is 28, and most of you got it right. So let's get into the solution, right? So a couple of things. The computer only allows 2 address instructions. That's one important thing, which means you have an opcode, right? You have where one operand can be register and another can be a memory location, right? So one is a register, the other is a memory location. That's important, right? Next thing that it says here is your 50 registers and 55 instructions. Okay, and what is your total memory size? 64 kilobytes. What is 64 kilobytes? 2 power 6 into 2 power 10, which is, this requires 16 bits now. By default, we assume everything to be byte addressable unless otherwise stated, right? So 16 bits you need, which means your memory location requires 16 bits because your memory is 64 kilobytes, right? Now, what about registers? You have 50 registers. Now, notice this. To address 50 registers, 5 bits won't be sufficient. 6 bits will be sufficient because 2 power 6 is 64, 2 power 5 is 32, right? So you need 6 bits to address 50 registers. So 6 bits will go here. Now you have 55 instructions, right? You have 55 instructions. Same logic. To write opcodes for 55 instructions, to write opcode for 55 instructions, how many bits do you need? You need 6 bits. Same logic, just like this, right? So this is 32 and this is 64. You can't do it with 5 bits. You need at least 6 bits to do it. So opcode is also 6 bits. So the question asks the minimum number of bits that are required. So 6 plus 6, 12. 12 plus 16 is 28. That's all. Fairly simple and straightforward question, right? So any questions that we could not answer in this session, again, I'm just showing you the email address. Please feel free to email us at gatecsc@appliedcourse.com. We'll try to answer all the questions as soon as we can, and we try to answer, I mean, even if you're not a course enrolled student, we try to answer as best as we can. Okay, cool. So thank you very much, and we have just finished it on time, and see you the coming Wednesday. Okay, bye-bye.